Hello and welcome back to the CCENT journey with me, Ryan, and in this section we're going to continue with Ipv6 part 2, focusing on the addressing. Now we're going to start off with a slide heavy, so very text heavy information, and then later in the video we're going to jump on the CLI and do some packet captures and configure RIPNG. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. So this slide is going to be very text heavy, but we need to work together and get through this because these are very important bits of information that we need to understand about the addressing scheme for Ipv6. Now it's highly recommended that you've watched the previous video prior to this one, because in the previous video we've talked about the Ipv6 format, how it actually is made up of the hexadecimals and how it reverts to decimal and so forth, and how it differs from Ipv4. None of that's going to be covered in this video. We're going to cover all the different addresses, or the different address types, like global, unicast, multicast, and so forth. So again, very heavy text slide, but we need to get this information out there and ensure that we understand it for the CCENT. So one key thing that I always like to mention about Ipv6, that is also true in Ipv4, but at CCENT level it's kind of a bit of an unknown variable. But ultimately the idea of an Ipv6, first of all, you can have multiple IP addresses per interface. Now at the CCENT level, I don't think we actually talk about what we call secondary addresses, because on a interface you can actually have multiple IP ranges, long as you put the word secondary on the end of it. However, in Ipv6 it's very common to actually have multiple addresses against an interface. In Ipv4, normally that's not the case. It certainly can be part of some designs, but in most cases with Ipv6 you're going to have more than one address per interface. So first of all, keep that in mind when we're looking at these different IP addresses. So the first type I want to talk about is something called a link-local address. So link-local is something we want to actually memorize, and something that we also want to actually memorize is the actual starting block for an Ipv6 address. So if you ever see anything with FE80, it's a link-local address. So that's a reserved 10 bits to create the FE80. Now it's automatically assigned with an Ipv6 host when it comes online. So that means if I have a PC or a router and they're connected together, if I were to turn on Ipv6 on both of these devices, they will automatically assign themselves a link local address on their network interface cards. And in fact, if you go to your PC now, like your Windows PC, and look at the ipconfig/or, you'll notice that you already have a link local address, because 9 out of 10 times your NIC, especially nowadays, is sent out Ipv6 ready. When you enable it on a Cisco router, you can actually see the Cisco itself assign a link local address to the network interface card. Now these link local addresses are only designed for communication between links. So what I mean by that is they're not routable between interfaces. And the reason I got think RIP here is because let's have a look at a network quickly. If we had 3 routers back to back and we have networks X and Y, when we're running RIP here, obviously we run RIP on all of these interfaces, and we enable that using the network statements. But what actually happens in Ipv6 is when that information is exchanged between routers, i.e. here's all the networks that I'm aware of, and can you pass it on to your neighbor and so forth, the source and destination of, the source, not the destination, the source of all this information is actually a link local address. So the actual link local address will create that RIP packet in the source, send it over to this guy. This guy will build that information inside its routing table, and then of course generate its RIP traffic or its RIP updates to be sent over to this router. Now the source will always be a link local address. The destination, just like in IPv4, is a multicast address. So link local is used for any traffic going between devices. It's not used to route. So if this guy over here, he will never learn the FE80 of this interface. The FE80 communication happens on a per link basis. Now along with link local, we have something called a unique local address. Now again, unique local addresses are not globally routable. However, notice it is routable, just not globally, meaning we can't put it onto the internet, but we can route it inside our private environment. So this is very similar to what we've learned in IPv4 regarding our private IP space. We learn in IPv4 and the use of NATs and so forth that we could actually create a network locally in our homes or in our businesses that can communicate using private IPs, but when it needs to communicate with somewhere on the internet, it needs to go through some sort of kind of network address translation in order to communicate with valid IPs on the internet. Well, unique local addresses aren't able to go onto the internet. They're very similar to these private IPs, and it's important that we understand the IP range that's been reserved for these individual addresses. So we've got FE80 is the main bit we need to worry about for link local, and for unique local it's FC00. So unfortunately, two things we're going to have to remember there about IPv6 addresses. So moving on, we have global unicast. Global unicast is what we have on our global routing table. So these are our public IP space. Now we have two ranges here that we need to remember. First of all, if you're applying for an IPv6 address today, you're going to see it start with 2001, and that's part of a /16, so the first 16 bits have been reserved. But that is of course part of a larger block of a /3, and this /3 is currently the global unicast block. So why bother giving out an entire /3 when we can again subnet it down further to a /16? So once that 16 is exhausted, we'll obviously move to something else inside that /3. And the last address overview that I need to talk about on this slide is multicast. Now, multicast, as we know in IPv4 conversations, is primarily used for things like RIP. You know, we had our routers connected together, and the routers were advertising networks to one another, and they were sending it to the well-known multicast address of 224.0.0.9. And if the router was running RIP, then it was listening on this IP address, and it was able to receive and deal with those routes that it was sending and receiving in RIP. Well, the same is true with IPv6. Notice that 224.0.0.9 becomes FF02::9, and what we do need to remember is anything with an FF at the front of it is going to be multicast, and it's a reserved address. And two important mentions here at the CCENT level is kind of two predominant multicast addresses, which is the FF02::1, which is for all host, and the FF02::2, which is for all routers. And you'll learn later that this is using the kind of like neighbor discovery in order for the network to self-configure itself. But the kind of FF02::1 is almost like a broadcast, but the term broadcast isn't used in IPv6 because we don't have any of the addresses that are very similar to 255. However, you could argue that, of course, if you're sending a traffic, a particular packet to all host, then it does count as a broadcast. But as far as the exam and as far as the CCENT is concerned, there's no such thing as a broadcast address in IPv6. We only use multicast addresses. So those are the main addresses that I want to talk about at this stage. So go back over it. Like I said, it was a text-heavy slide. We got Link-local. It always starts with the FE80s. It's automatically assigned when you come online, and it's used for communication between devices. So things like RIP would use it to communicate. Unique local address starts with the FC00. It's not globally routable because it's the equivalent of our IP space, our private IP space. Global unicast is the opposite. It's our public IP space. It is globally routable, and currently inside that 2000/3, we're giving out 2001/16. And then our multicast, this is used to kind of for the control plane primarily, at least at the CCENT level, that's how you learn it. Things like RIP, which used the multicast address of 224.0.0.9 to communicate at IPv4. In IPv6, we use the FF02::9. And anything that starts with the FF is reserved addresses for multicast. And there are many things multicast is used for, like, for example, to send communications to all the hosts on the network, or to send communications to all the routers on the network. So now we're going to jump across to a network I've got set up. This network is actually part of a ongoing lab I have going on. So let me just clear the configuration on everything. Okay, so we've got all the configuration blanked out on all 10 of these routers. Obviously, we're not going to use all 10, but what we're going to do is just go onto one of these routers and actually configure IPv6. So on router 1 then, we're actually going to create a interface, and that interface is going to be a sub-interface of, let's say, VLAN 20. I want to give that an IP address. Let's say, let's make it part of a /24. And then we're going to go across to router 2. Oh, sorry, not 192. Right, and then we're going to see if we can ping each other. So can 1 ping 2. Great. So we've got IPv4 communication there on the gig 1.20 interface between router 1 and router 2. So now what we're going to do is enable IPv6. And we're actually going to use the link local addresses, just as we discussed previously, but I'm not going to actually assign it. I'm going to allow the router to automatically assign it using something we've not discussed yet called EUI, the Extended Unique Identifier. So I'm going to go down here, I'll do Ipv6 Enable, and I'm also going to enable Ipv6 unicast globally. This is an important command. Some platforms it's not on by default, and what that will do is kind of prevent you from routing IPv6. So what I mean by that is some platforms will not allow you to assign an IPv6 address, but more likely they will allow you to assign an IPv6 address, but when you enable something like RIP or try to pass IPv6 traffic through a router, it won't work as expected. So make sure that before you do anything with IPv6, you enable the unicast routing feature. Now what if we go over to this guy, and I'm going to enable that unicast feature, and I'm going to enable the interface for IPv6. Now we look at the running configuration of the interface. We can see we have Ipv6 Enable and we have an IP address on the interface. Now we know IPv4 is reachable because we've tried that pinging and we saw that. And if we do the show IP interface brief, we can see that it's up. But what we need to do is pop in Ipv6 Brief, and notice something very interesting here. All our interfaces are unassigned apart from the one interface that we enabled IPv6 on. And also notice something very interesting. The beginning of the address is FE80. So by doing the IPv6 enable, what's happened is router 1 and 2 is assigned itself an IPv6 address and is able to communicate already on the wire with each other. So what do I mean by that? If I go back to the router 2, you can also see router 2 is assigned itself an IP address. So if I grab this address, go to router 1 and ping it. It's asking me for the outgoing interface. Oh, I didn't put the word Ethernet. And now I've specified the outgoing interface is able to ping out that interface and reach the final destination, which is of course router 2, despite the fact I didn't actually put an IP address on the interfaces. And that was again the EUI64 with a combination of the Link-local, able to kind of assign itself an IP address, use something called DAD, duplicate address detection, to find out that no one else is out on the network using the same IP address, and then it's able to assign itself and we're able to communicate with the rest of the network. So that was kind of two functions there. Now I did say that you can have multiple addresses of IPv6 on an interface. So despite us having a Link-local, we can still go under here and assign us a IPv6 global address. So let's say, for example, we'll just say it's 2001. We're going to use colon, and remember that means that there's a bunch of zeros. And then we're going to use the word beef :1/64. So that's the IP address that I'm going to give it on this side, and over here we're going to increment this by 1. So remember, if you wrote this out long-handed, it'd be 2001. So technically this is a global unicast address, colon, which means all zeros, and then we've got the word beef :, and then 2. So there'll be 3 zeros there because obviously we've omitted it using that colon. Leading zeros have been omitted. /64 tells us that the first 64 bits of this address is the network portion and the last 64 bits is the host portion. And now router 1 and router 2 have an IPv6 address. And if I do the show IPv6 in brief, you can see that this interface now has 2 addresses, both the Link-local and the global unicast that I've assigned. And then if I were to ping it, I can ping it locally, and I can ping the remote end, which is of course router 1. So what we can see here is we have multiple addresses on the interfaces, and of course we can see between router 1 and router 2 that they're able to communicate over both of those addresses. Now if we were to form some sort of RIP between them, some sort of neighborship if you like, would we actually, when we exchange the routes, what exactly would it look like inside the packet? Well, we can look at that together. Okay, so the way we're going to do a capture is these are actually CSR 1000 running XE. So they're a cloud services router and they're spun up on a VM machine, and they support the embedded packet capture, which means that we can do a PCAP, like a Wireshark, on the box itself and export it and look at it. So what we're going to do is set up a packet capture, and then we're going to set up a RIP very quickly to end the video. So something relatively interesting to end on. So first of all, and as a side note, the PCAP config that I'm about to show you now is outside the scope of the CCENT, but it's something that's quite interesting to look at. So we can do monitor capture. We're going to give it the process of 1. We want it to match IPv4, any source, any destination, and we do monitor capture 1, and then we want to do it on the interface that we created earlier in both directions, and then we're going to actually start that capture. So now router 2 is looking on gig 1.20 for any IPv4, which won't help us in this scenario because we want IPv6. So what I need to do, is quickly stop the capture, replace the filter and start the capture. So IPv6 is now being captured on gig 1.20 out router 2, and anything that we do on that interface will be captured in the buffer, and then once it's in that buffer on router 2 we can export it. So what we're going to do now is simply enable RIP for IPv6, which is of course RIP next generation. So config D, for RIPNG we enable it on the interface. So IPv6 RIP, it asks us for a name. Let's just call it test, and that's the process, and we want to enable IPv6. And then we go back to router 1. So now we have RIP running back and forth on router 1 and router 2. And then what I'm going to do is on router 1, just so we have something that can be advertised, we're going to create a IPv6 address. Something like, oh sorry, it's overlapping. Let's just do something like that. And then what we're going to do is put RIP also on this interface, because again, unlike the global process for IPv4, for RIP IPv6 we have to do it on a per interface basis, which means we have to put it on the loopback address. So IPv6 RIP, and then we have to call it the same process, which was test, and now hopefully router 1 will be advertising that loopback to router 2 via RIP. And if we do show IPv6 root, rightly so, we can see in our table via RIP that 2002/64 that I configured. Okay, excellent. If I now do monitor capture stop, that's going to stop the capture, but it's going to keep all the information we had inside a local buffer. Now I need to export that buffer. So here we're going to do monitor capture 1 export. We're going to export it using TFTP. We're going to pass it to 192.168.0.50, and we're going to call it RIPNG.pcat. So the export is now successful, and if we go to where the export is going to take place, we can see the RIPNG packet capture here, and if we open that up, we can see that there is a bunch of RIP information that's being sent back and forth between the two routers. And if we filter out, what's interesting here is the source and destination of the RIP traffic. Notice that the source is the FE80, which is the Link-local, and the destination is that Multicast address. So it's important that we know that even though at the moment our routers have both a global unicast and a Link-local, the Link-local is used to exchange that information between each other, and of course the destination being that being that multicast address of the FF, as we would expect. And if we were to expand it, we can see what routes are actually being advertised, and you can see it's that loopback address we created on router 1 being sent across to router 2 as a network update. Okay, so that's what we've got time for in this lesson. Just to kind of recap what we've done. We first of all talked about the different address types that we need to remember, which is those link locals, unique local, global unicast, and multicast. Now, like I said, it's very slide heavy, but it's important that we understand the differences between these, and of course memorize why they're different. So link local is kind of use those FE80, and they're generated automatically when using the IP enable with the help of the EUI64, the extended unique identifier. Now this is something we've not talked about yet, both of these in fact, but we will have a video on it. But ultimately what happens there is the link local address looks at the MAC address of the interface, and from that is able to build an IPv6 address for itself. It then does what we call a DAD, a duplicate address detection, to which it sends out a solicitation asking if someone else in the network has that IP address. Of course, no one is going to have that IP address because in theory all of our MAC addresses are unique, and as such that IP address is then assigned and communication can happen on the wire. And we saw that. We've done the Ipv6 enabled and we're able to ping between the two locally connected networks. We briefly talked about Ipv6 routing. We said that if you don't have Ipv6 routing turned on, then you may be able to have interfaces with Ipv6, but when traffic tries to flow through the router, this traffic will fail. So it's important that as a habit, we turn on the Ipv6 routing if we were to configure Ipv6 on our networks. And if we were to get some sort of question around maybe we've assigned some Ipv6 but it's not working as expected, then maybe a good culprit is to ensure the Ipv6 routing is enabled. We then dived into a PCAP, a packet capture, and we saw the RIP next generation protocol actually exchanging information using the Link-local, despite the fact that we had a global unicast also assigned on the interface. So we now know for sure that Link-local is what's used for communicating between devices on the wire for control plane information like the RIPNG updates. We also see multicast. These are the FF. So for example, we saw FF02::9 used as the destination address in the PCAP for RIPNG. I hope this has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.